In this video, we're going to look at long division as an algebraic technique for integration. Now, when we see an integral of a rational expression, we have several choices for techniques that we could apply. But when the exponent in the numerator is greater than or equal to the exponent in the denominator, long division is often a really good choice. And in this case, my exponent in the numerator is greater than the exponent in the denominator, so we're going to apply long division. So I'm going to divide these two polynomials, x plus 1, we're going to divide into 2x squared. Notice we're missing an x term in this polynomial. I'm going to add in plus 0x as a placeholder, and then minus 4. Now, long division with polynomials works a lot like it does with numbers. I want to decide what I can multiply times x plus 1 that's going to get me to cancel out as much as possible here. But specifically with polynomials, what we want to do is cancel out that first term. And so I want to ask, what do I multiply times x to get 2x squared? And in this case, that would, of course, be 2x. And I'm lining it up in the x column. So 2x times x is going to give me 2x squared, and 2x times 1 gives me 2x. Now, just like in normal long division with numbers, we're going to subtract. So I'm going to make this minus and make that minus also. We've got to distribute that subtraction to both terms in our polynomial here. 2x squared minus 2x squared. Those, of course, are going to zero out, which is what we want. And then I have 0x minus 2x, which would, of course, be negative 2x. And I'm going to bring down the next term in the polynomial. So this time I want my first term, negative 2x, to cancel out. What do I multiply times x to get negative 2x? That would be negative 2. And negative 2 times x is negative 2x. Negative 2 times 1 is negative 2. I need to subtract this polynomial, so I'm going to distribute that minus sign, which will make this plus and make that plus. Negative 2x and 2x, they zero out. Negative 4 plus 2 is negative 2. And so this negative 2 is going to be my remainder, minus 2 over, or still divided by, x plus 1. So now that we've divided these polynomials, the purpose of doing that is so that I could rewrite this expression into something that I can integrate. And this is how I'm going to rewrite it. This integral is equal to the integral of 2x minus 2 over x plus 1 dx. And now I have an integral where I can apply my antiderivative rules and integrate. The integral of 2x is, of course, x squared. Integral of minus 2 is minus 2x. And the integral of 2 over x plus 1, hopefully you're seeing that in a kind of 1 over x form, except that it's x plus 1 down here. So we can think about it like a u substitution. But if I let u equal x plus 1, my du is just equal to dx, excuse me. And so there's nothing, no extra substitution that we need to do there to make the u substitution happen. And so we're just going to kind of do that u substitution in our heads and say this is minus 2 times the natural log of the absolute value of x plus 1 plus c. Now, if I lost you a little bit there on the integration of that last term, go back and review integration by substitution. All right, I'm going to do one more example for us, the integral of 5x squared divided by x squared plus 1 dx. In this case, the exponent in my numerator is equal to the exponent in my denominator. This is still a time when long division is an option for us as an algebraic technique. So as I set this up for long division, notice that we're missing an x term in the denominator. And in the numerator polynomial, there's no x term and there's no constant term. So we need to be aware of that as we set this up. X squared plus 0x plus 1. And we're going to divide that into 5x squared plus 0x plus 0, putting those 0 terms in there for all the placeholders that we need. Okay, so as I divide x squared plus 1 into 5x squared, I'm going to ask myself, what do I multiply times x squared to get 5x squared? And that, of course, would be 5. And since it's just a constant, I'm going to put that over here above the 0 in the constant column. 5 times x squared, 5x squared, 5 times 0x would of course be 0x, and 5 times 1 is 5. And now we're going to subtract. I'm going to make that negative, my 0 negative, not that that really matters, and then the 5 also becomes negative. 5x squared minus 5x squared, those terms 0 out. 0x minus 0x is still 0x, and 0 minus 5 is minus 5. And since that's the last term right there, this is going to be my remainder. So minus 5 over x squared plus 1. Now that we've divided it, we can rewrite the original integral. This is going to become the integral of 5 minus 5 over x squared plus 1 dx. And now this is in a form that we can integrate, although I have a feeling I need to remind you about a derivative rule that we're going to inverse now so we can use it as an antiderivative rule. Remember that the derivative of inverse tangent of x is equal to 1 over x squared plus 1. And so that means that the integral of 1 over x squared plus 1 dx is equal to inverse tangent of x. And if you notice, that's what we have here in our second term here that we're integrating. So if I integrate, the integral of 5 is 5x minus, and here we're going to use that inverse tangent rule. We are multiplying by 5, so that 5 is just going to stay, times inverse tangent of x. And then, of course, we need a plus c because this is an indefinite integral.